All right, so we introduced in class recently the idea of a capacitor. And a capacitor is two conductors with equal and opposite charges. And in particular, we looked at one geometry called the parallel plate capacitor. So this is a capacitor that's made up of two infinite plates, both conductors. And in this case, I'm going to charge up the top one to some positive Q. So that means it has positive charge on the top plate. And the bottom one will then be at charge negative Q, which means it has some negative charge on the bottom plate. And we've seen that this establishes an electric field between the two plates that's uniform everywhere between the two plates. And in this approximation where we ignore edge effects, we'll say it's 0 outside these two plates. And then we saw that we could define this capacitance. And for this particular geometry, the capacitance is equal to epsilon 0 times the area of the plate. So this is the area of each plate divided by the distance between the two plates. And then we said, well, we can think about how much energy does it take to charge up these two plates. And that's equivalent then to the energy that is stored inside the two plates. And we saw that the energy stored is equal to 1/2 this capacitance times the potential difference between the two plates squared. So now we can think about what is this potential difference. So this potential difference, and again, here all we care about is the magnitude. So the magnitude of this potential difference, because this electric field is uniform, this magnitude is just equal to the electric field times the distance between the two plates. So now we can take what we have over here and we can put it together and see what we can extract about the energy that's stored in this configuration. So let's put all this together. I'll say that the energy that's stored is equal to, and let me plug it all in. I have 1/2. My capacitance is epsilon 0 times the area of the plate divided by the distance between the two. And now I have an expression for my delta V, and that is just electric field times the distance squared. And now all I'm going to do is I'm going to rearrange this a little bit. So let me pull out a 1/2. I'll pull out the epsilon 0, and I'll pull out the E squared. And you see then what I get left with is just the area of the plate times the distance between the two plates. So now I can stop and think, what is this telling me? Well, this area of the plate times the distance between the two plates, what that really is the volume between these two plates. So it's the area times the distance, that's the volume between the two plates. Or in this example, it's the volume where the electric field is non-zero. That allows us to think of this then. So if I can rewrite 1/2 epsilon 0 E squared times the volume where the electric field is non-zero. That allows me to define this as what we're going to call an energy density. Energy density. The reason for that is to get the total energy, you multiply the energy density, or energy per volume, times the volume. So this is important enough that we give it its own symbol. So this is a lowercase u now. The energy density, we say then, is equal to 1/2 epsilon 0 times E squared. And this has units of joules per meter. So now everything I've done so far is for this very particular case of a parallel plate capacitor. But what you can actually derive is that this expression, this energy density, is generically true for any capacitor that we want to define. So you can think of the example we did where we did two spherical shells as a capacitor. And so in general, if you want to find the energy that's stored in your capacitor for any generic geometry, you would say that the energy that's stored in your capacitor is then equal to the integral of this energy density times the volume. And let's stop and think what volume we're integrating over. You want to integrate over the volume basically so the volume where the electric field is non-zero.